Here we have our system. We have an inertial frame where all of motion is in an E1, E2 plane. We are going to describe the position of our particle of mass m via polar coordinates r and theta. And because all of the motion is in 2 dimensions, we can write down the Lagrangian as m over 2 times the velocity squared, magnitude, which is r dot squared plus r squared theta dot squared, that we've derived many times before, minus our potential function, which we will call v. And because this is a case of central force motion, v is a function of the radius magnitude r only. As we have previously seen, this system is cyclic in theta. And that means that the system is invariant under rotation about E3. That means that we expect the conjugate momenta for the generalized coordinate theta, p sub theta, to be a constant of motion. And when we evaluate it by taking the partial of the Lagrangian with respect to the time derivative of the relevant generalized coordinate, so that is the partial of the Lagrangian with respect to theta dot, we find that p sub theta is mr squared theta dot, which is the magnitude of the angular momentum, which is, of course, a constant of motion. P dot theta will be the time derivative of this, which will be equal to the partial of the Lagrangian with respect to theta, which is 0, because the Lagrangian is independent of theta. So we've now rediscovered the conservation of angular momentum and therefore Kepler's second law. We are now going to apply the Euler-Lagrange equations and write the time derivative of the partial of the Lagrangian with respect to the time derivative of our first generalized coordinate r minus the partial of the Lagrangian with respect to the same generalized coordinate is all equal to 0. And that works out to the time derivative of mr dot minus mr theta dot squared plus the partial of our potential function with respect to r. This term is just mr double dot under the assumption that the mass is constant. This term remains mr theta dot squared. And we are going to define negative partial v with respect to r as some function f of r. So there's times -1. In here, we bring it over to the other side and define this as f. We've already stated that h, the magnitude of the angular momentum, is mr squared theta dot. And therefore, mr double dot minus h squared over mr cubed is equal to the function f of r, which is negative the partial of the potential with respect to r. Energy is conserved in this system as there's only a time-independent potential, and therefore we can write the total energy as the sum of the kinetic and potential energies, which works out to 1/2 mr dot squared plus h squared over 2mr squared plus our potential function v of r, and this must be a constant in time. We can solve this directly by quadrature, where we define u as 1 over r. That is, for all time, the angle theta is given as its initial value theta naught minus the integral of a dummy variable u integrated 1 over the square root of 2m e over h squared minus 2m v over h squared minus u squared from the initial value of u to the current value of u. If v of r is a power law, then this expression is exactly solvable by an elliptic integral. And what we find in that case, the second derivative of u with respect to theta plus dummy variable u is equal to -m over h squared, the derivative in u of the potential function, which is a function of r and therefore a function of 1 over u. This statement directly gives us our equations of motion for this two-dimensional central force system. Now we're going to apply Hamilton-Jacobi. We have our original conjugate momenta, p sub theta, which is the partial of the Lagrangian with respect to theta dot, and is equal to the angular momentum, mr squared theta dot, and p sub r, which is the partial of L with respect to r dot, and is just equal to mr dot. The Hamiltonian of the system is therefore 1 over 2m times the quantity p sub r squared plus p sub theta squared over r squared plus the potential function. And the Hamiltonian in this case is equal to the total energy of the system. And so we will call the Hamiltonian the constant alpha 1. As a quick aside, we wrote this down by inspection, but you can verify this by formally applying the Legendre transformation to the Lagrangian, and I urge you to do so as a check on your understanding. Because theta is cyclic and p sub theta is constant, the characteristic equation is easily separable. And so our Hamiltonian characteristic function W can be written as a function W1 of R only plus the conjugate momentum associated with the theta generalized coordinate alpha sub theta times theta. And remember, this is the transformed conjugate momentous. This is the capital P sub theta. Hamilton-Jacobi equation therefore becomes the square of the partial of W1 with respect to R plus alpha theta divided by R quantity squared plus twice the mass of the orbiting particle times the potential function V of R must be equal to 2m alpha 1. And we have applied this 2m term to both sides to just cancel out some of the things in the denominator here, which means that we have to carry 2m times the Hamiltonian on the right-hand side. Alpha 1 is equal to the Hamiltonian is equal to the total energy of the system. The partial of that W1 function, which is a function of R only with respect to R, is equal to the square root of twice the mass times quantity alpha 1 minus the potential function V of R minus alpha theta over R quantity squared. And that means that our full generating function, the characteristic function W, which must be equal to the antiderivative of the derivative of W1 in R with respect to R plus the alpha theta theta term, can be written as the derivative in R of the square root of 2m times the total energy, which is alpha 1, minus the potential energy, minus quantity alpha theta over R squared, plus the alpha theta theta term. And from this, we now get our new generalized coordinates. Q1 maps to beta 1. And so from our previous result, we can write the time plus beta 1 is equal to the partial of our characteristic generating function with respect to alpha 1, which is equal to this integral. And this expression is exactly the same as Kepler's equation or Kepler's time equation. The time plus a constant is equal to the integral of dr over the square root of twice the mass times the kinetic energy minus our constant alpha theta over R squared. You should all stare at this until you've convinced yourself that this is in fact Kepler's equation. And then the only other remaining generalized coordinate, beta 2, is equal to the partial of the generating function with respect to alpha theta and gives us exactly the same elliptic integral as we found before. So we've essentially rediscovered exactly the same equations that we've already had. So what exactly was the point here? The point of all this is that this formalism actually gives us a powerful way to handle perturbations. Let's consider a perturbation to our original Hamiltonian. And so we write a new Hamiltonian to this system. That is, our new Hamiltonian is the original Hamiltonian, which we'll call H naught, which was independent of time, plus a small perturbing Hamiltonian, which is a function of the original phase space and time. As before, the unperturbed Hamiltonian results in Hamilton's characteristic function W of alpha and Q only. And we know that the original Hamiltonian expressed as a function of the original generalized coordinates and the partial of the characteristic function with respect to the generalized coordinates is equal to that original constant alpha 1. All of the transformed conjugate momenta can be written as partials of the separated characteristic function bits with respect to their respective generalized coordinates. And these are all the other alpha I constants. And all of the transformed generalized coordinates are partials of the characteristic function with respect to the alphas, and they are themselves the constants betas. So we have this really nice, completely constant representation of the original Hamiltonian. The new Hamiltonian, K naught, is still alpha 1, and when perturbed, becomes the alpha 1 constant plus the perturbing Hamiltonian H1 expressed as a function of the constants alpha, beta, and time. The transformation is itself canonical, so Hamilton's equations exactly apply. What does that mean? Well, that means that the time variation of our previously constant conjugate momenta the alphas must be negative the partial of the perturbing Hamiltonian with respect to the betas, and similarly, the time derivatives of the betas must be the partial of the perturbing Hamiltonian only with respect to the alphas. And the only caveat here is that the first coordinate is 1 plus the partial because we had that single term of time in there. Small perturbations in the Hamiltonian result in small variations of previously constant canonical variables. And this should be starting to sound very familiar because this is exactly the approach that we've been taking to the variation of orbital elements in the two-body problem. H1, this perturbing Hamiltonian, can vary in time in very complicated ways. However, we can always average over these alpha.I and beta.I expressions to find average secular variations of variables. And this is going to be an incredibly useful tool for us that we are going to say a lot more about soon.